Solve the recurrence relation an equals 5an minus 1 minus 6an minus 2 for n greater than or equal to 2 with the initial conditions a0 equals 2, a1 equals 10. First we determine term a2. Replace n with 2 in the recurrence relation. You get this. And a1 is 10, a0 is 2, so we obtain 38. A2 must be 38. If we wish, we can compute A3 similarly, but we are doing this just for a check. At the end, we want to check if our formula is good. 2. The characteristic equation. From here, replacing A2 with r squared, A1 with r, and A0 with r to the 0, r to the 0 is 1, we obtain this. This way we are looking for a solution of the recurrence relation only in the form an equals r to the n. So this is the characteristic equation. We write it in equivalent form, the standard form of a quadratic equation. And then we factor the left-hand side to find the zeros. Or you can just use the quadratic formula to find the zeros. It turns out that there are 2 and 3. In the next part, from the roots, because they are different, we determine that the first theorem applies, the first theorem of section 8.2. If we have repeated roots, then we will use the second theorem. Here, different roots means first theorem. And then we find a formula for any solution that satisfies the recurrence relation only. Any recurrence relation that any sequence that satisfies the recurrence relation has this term an equals c1 2 to the n plus c2 3 to the n, where c1 and c2 are some fixed constants. To satisfy the initial conditions, we replace n with 0 here. A0 is this, and from the beginning we know that A0 is 2. This is C1 plus C2 equals 2, and from the second initial condition, when n is 1, we obtain this. N is 1, so this 2 and 3. And A1 from the beginning is given to be 10. So we have this system. Solving this system, we'll find the correct values of the constant C1 and C2. Multiply the first equation by -2 and add the result to the second equation. You'll get 0, and this will be 3c2 minus c2, so just c2. -4 plus 10 is 6, so c2 is 6, and c1 can be computed from the first equation. 2 minus c2 is c1, so c1 is 4. Replacing the constants here with the found values, we obtain this nth term for the uniquely determined recurrence relation, that's sequence that satisfies the recurrence relation in the initial conditions. And in step 5, we check what value will produce this formula when n is 2. A2 is this, replace n with 2, and the result is 54 minus 16, 38. So we have the same value that we computed in the beginning, which suggests that our formula is correct. If we don't have errors, theorem 1 guarantees that the formula is correct.